we chose our topic. We chose this topic because we both own dogs, we love dogs, and we enjoy playing with them. We knew that this topic would keep us interested and entertained, and it would be fun to study. We found that there was a lot of calculus behind playing fetch with a dog because it creates a curve that we can derive many analyzations, such as velocity and acceleration, from that curve. So, keep continuing. This was our inspiration. This is my dog, Murphy. He's a Lhasa Apso, and he's 10 years old. And then this is my dog, TJ. He's a Cairn Terrier, and he's 8 years old. And then, more inspiration. This is Murphy running, playing fetch. Back when he was younger, because now I tried to get him to play fetch and it didn't work. He's too old. There we go. So, more inspiration because he loves to play fetch. Yeah, so not really a curve, but you kind of get the idea of where we were going with this. So, the history of our topic.
Okay, so dogs are descendants of gray wolves. So, like wolves, they're very social and like to be around humans. They became domesticated in Central Asia around 13,000 BC, and they became acquainted with humans 10,000 to 15,000 years ago. And living around civilizations of humans, first humans tried to scare away dogs, but then they realized that they were friendly and were used to actually keep society healthy. And so humans began to encourage the presence of dogs and began to train them. And then dogs enjoy playing fetch because it's relatable to like chasing small prey.
So how we went about our project. First we were like, we want to create the curve and we want to get the equation, but there was a lot to do before we got to that point. So with Ms. Burnham's help and Mr. Zimple's help, we set up in Mr. Zimple's room on his white backdrop. We set up an iPhone on a tripod, put yardsticks on the background, which you'll see in a little bit, and then multiple test throws before we actually got going, and then took a slow motion video. And then we took screenshots of the video 36 times so that we could piece them together and get the arc. And so then we layered the pictures over each other in Photoshop to create a picture of the arc that the ball made so that we could make the equation. We sped up the slow motion video to get the real time so that we could do a time and distance graph. We found that the total time we took and how many intervals we could fit into the time frame. So we used 30 intervals because it's only like a second long from point to point. We divided the total time by the intervals to get the x values of our points. Then we used the yardsticks to determine the height, and this gave us x and y coordinates. We used time and distance to plot points in a graph, and we used the points to make an equation, and then we did many different calculations. So this is like an overview, and then we're going to show you what we did.
Yep, so then this is going to be the first video. This is a slow motion video. So you'll see that the yardsticks will be in the background, and then Maddie is throwing the ball, and then it will create a little curve.
So there it's going, and then this is what we use to get our equation of position.
And then in the back there is measurements, and we have a picture so that you can see the measurements better.
And then, so that was slow motion. And then this is real time. It goes super fast because like I said, it's like a second. But this gave us like 1.11 seconds, which was our graph. There it was. I'll watch it again. So that's our time. And then this is the picture that we took. We overlaid our screenshots to get the curve. And so then I was standing here, and I bounced the ball, and it made a curve, starting at 0 seconds to 1.11 seconds. And then the yardsticks are measured here. And so you can see that it's maxed out at like a half a second at about 100 centimeters. Yeah.
So then using this picture, then we were able to, on the next slide,
Yep.
Plot a graph using coordinates. And so we actually put this in Excel, and then it generated a graph for us.
Yeah, so then time and distance, same thing. It was the same as this picture, just this is real life, and then this is what you see every day in calculus. So the mathematics that we found from that graph.
So then using the graph, we were able to get x and y coordinates on the position function. And we wanted to find the velocity function, so then we wanted to find the x and y coordinates on the velocity graph. And in order to find these coordinates, we use the slope function to approximate the slopes of the tangent lines on the position function. So we use the slope formula, and for example, this is the position of the tennis ball, the coordinates, and we use the first two coordinates just for like an example. And between that, we figured that there was a velocity of 243.243 centimeters per second. And so then we actually did this all in Excel, so once we did one formula, we could actually drag it down and then it would do it the rest for us. So then this is the velocity table, and again, you'll see that between the first 2 points is the previous number that we had on the other slide. And so then we actually plugged all of these coordinates into our calculator, and we plotted them. And then we used a regression line to come up with an equation of the data points, and we chose a Porter regression line because that's just what best represented the data. And then also just another thing to point out, you'll notice that like around about half a second, the velocity starts to turn negative because it's actually changing direction.
So this was the velocity function that we got from the calculator from that regression line. And so it's pretty long because it was super detailed because we gave it like the 30 to 36 points. So velocity is the speed of the ball in a given direction. And we know that because it's the derivative of position as it keeps going down. So we use velocity, we can get acceleration, jerk, total distance traveled by the ball, and average speed. So the acceleration equation is just the derivative of velocity, and acceleration is the rate of change of the ball, of the velocity of the ball. So this is our acceleration equation, and this is the graph of it. And okay. And then we took the derivative again to get the jerk equation. Now you're probably wondering what the heck is jerk, just like Claire was when I said it's the derivative of acceleration. Like, it's a thing. We don't use it in calculus very much, but it's more used in physics. So the jerk of the ball is a quick, sharp, sudden movement. It's the derivative of acceleration, which gives the rate of change of acceleration. This is given by the equation here, and it looks similar to our position graph. Total distance traveled by the tennis ball. First, we had to find the roots of the velocity function, or where it crossed the x-axis. Right there. This is found at about a half a second, and our function ends at about 1 second. So if we integrate from 0 to half a second, from half a second to 1 second, because it's positive and negative, we will get our total distance, but we have to keep in mind that we have to take the absolute value so that we don't have a negative distance. So here's the integration from 0 to half a second, and half a second to 1 second. And this gave us 105, and this gave us a negative 100, which makes sense because it went negative. We get a total of 205 centimeters.
So then using the total distance traveled, we were able to figure out the average speed, which is distance traveled divided by the time of travel. So then using about 205.399 centimeters, and then again just over a second, we were able to get an average speed of 184.878 centimeters per second. And this is relatable to the distance traveled because they're similar numbers, and because the time of travel was just a little over a second versus the average speed is just 1 second.
So the history of the mathematics that we just used.
So mainly we were using speed, velocity, and acceleration. Galileo and Newton were main contributors to these three relatable functions. So acceleration is the rate at which an object changes velocity. And Galileo actually observed objects rolling down different inclines, and he developed the first correct concept of accelerated motion. And then Newton considered acceleration due to gravity, which is an unbalanced force. So then he developed his three laws of motion, which set the basics for velocity and speed functions. And then his second law, an object with a certain velocity maintains that velocity unless a force acts on it to cause an acceleration, was applicable. And also using his laws, the motion of an object can be solved using knowns such as displacement, time, acceleration, initial velocity, and final velocity.
History of the jerk equation. Claire said that I had to do this because this was my deal. So going over it again, jerk of a ball is a quick, sharp, sudden movement. It is the rate of change of acceleration, or the third derivative of the position function where we started. Due to Newton's contribution to acceleration, the jerk function originated from the derivative of the acceleration function. So basically because Newton dealt with acceleration, jerk followed. And then J is a common abbreviation for the jerk equation, mostly used in physics. history of derivatives and integrals. Leibniz used dy and dx for differentiation, also used derivative of antiderivative of x for integration. Newton computed a table of antiderivatives, and he also used substitution, which is kind of what we did. So how the math is applied. Position, you can use the position of the ball and compare it to the dog to see if the dog can keep up with the ball, like almost like related rates. You can work on velocity with your dog, which can come in handy when hunting, running, or fishing to see how fast they speed up in a direction. Acceleration, this relates to dogs, because you can work on different drills, such as working on changing direction while running at a certain continuous rate. Jerk, again, if you wanted to work on reaction time or agility, quick, sharp movements, you can make sure that the jerk of the ball is faster than your dog so that it's forced to go fast. Total distance. Depending on the distance of the ball and the terrain of where the ball is thrown, observations of a dog's choice of direction can be drawn. For example, dogs try to minimize the time that it takes them to get to the ball. Dogs unknowingly do this by minimizing the distance that they have to travel to reach the ball. And speed. If you wanted to challenge a dog, one would increase the speed of the ball so that the speed is greater than the dog to work on all of these drills.
And then just like one thing to add, we actually read an article about a guy who threw a ball in the water and that he noticed that his dog knew not to run in the water because it actually slowed him down. So he chose to run more on sand, which is kind of just showing that dogs unknowingly do a little bit of calculus in their head. And then he actually computed using Pythagorean theorem or something like that, how much faster it was actually that the dog chose. He always chooses the fastest route.
So dogs do calculus, just like us, relating back to our total distance that we found. And then other applications of these mathematics are basically just throwing a ball like we did and finding the equation of that art. Basketball, football, baseball, soccer, golf, tennis. That's what we did. And then that's the end of our presentation.
All right.